Welcome everyone to the fifth Race Online seminar of 2021. Today, Ahmed will talk about blockchain for decentralized learning. Ahmed, you're good to go.
Thank you, George. Hello, everyone. Today, I'm going to talk about blockchain decentralized learning. It is the secondment I am currently have with Untitled University, with Ahmed from Untitled University. And I hope that you find these slides, you enjoy the slides, you find them intuitive. So let's start by a little background about how a centralized AI centralized solution usually work. So usually we have a model publisher, which is the company. The company has a model, and then they collect the data from their customers, use this data to train the model, and then share the results back to the clients or the customers. But and you, as a customer, you kind of obligated to share your data. Otherwise, you're not going to get the service, right? And example of decentralized solution, we can see them around us from the big corporates like Google, Amazon, and so on. But there is some challenges that we need to tackle in this slide. First, from the consumer's perspective, there is a concern of a data privacy because you kind of obligated to share your data, right? Another concern is you don't have any control over the learning process, how the model trains on your data. There's no guarantee over of the quality of. You don't have a at least direct guarantees over the quality of the services provided by the companies. So yeah, and for the company or the let's say model publisher side, there are some challenges too in that model. First, they need to have an infrastructure to host a big amount of data usually to do the training. And also there is an unfair competition issue because new companies or newcomers usually need to have enough amount of data to start the training, to kick off the training, their models, right? That usually require enough customer bases, enough market share to actually start providing good services. A third challenge for the company is like the legal liabilities, because now you store the data of your customers, so you need to have to worry about the what legal burden, the copyrights of how I store them, how to use them, and so on. And this is a background of what's happening, at least up to this moment. And over time, there have been alternative solutions for that. First one is Federated Learning, introduced by Google, and I believe you guys familiar with that already. So, but let's recap over it. So we have a Federated Learning. It's a distributed learning framework. And what happens in this scenario? The model publisher, which is again could be a company, they have the model. But what changes from before is that they share the model with the consumers, people who have the data. They are like the data providers, also the people who can consume the model and train it. So they take the model, everyone train it on their own data, and then share back the weights. Okay. So now the training itself happens locally, but the aggregation, which weights to be considered, how to be aggregated, is still done by central authority, which is the company itself. Okay. So yeah, so we have local training updates, yes, but the aggregation is done by the global updates. That means still there is one global update over time, and there is one point that controls which weights to be aggregated, right? And that means they have the control still over the training. Some issues has been already solved, in my opinion, by using this federated learning approach. First, the training load is now distributed among the consumers. You don't have to worry about having a serious infrastructure for training. And it's one step. Let's say it's one step towards data privacy, because now you don't have to actually share your data, but rather train the model locally on your data and share only the weights of the model, right? now you don't have to worry about, as a company, you don't have to worry about the legal burdens of having from having the data, because you actually do not have them, but there is still some issues remaining. First, as we said, the control over the learning itself is done by one end. It's central control learning, and this architecture might might already cause some issues with training. We'll talk about them later. And there is still the unfair competition or the cold start problem, because you still typically, when you use that, you need enough customer phases that are willing to do the training for you, right? Um, so that led us over time to gossip learning too. So it's like alternative. It's not over time. It's like another alternative way to do the learning. And gossip learning is peer-to-peer actual learning. So we have a network of the data providers, the model consumers. There is no authority there. There is no one to control who how to aggregate the weights from the people, which weights to choose. Rather, each node of these train it locally, and typically they talk to each other. Like typically they talk to one of them. So you have the learning happen in the entire network, and that should be very fast. But there is still some challenges. Let's see first what they solve it. First, the updates are done locally, and the aggregation is done also locally, unlike the federated learning. The issues that have been solved by this I would like to think it's a better distributed learning paradigm, in a sense that it's faster in learning. Okay. Um, but and there is no localization like before, no call to start problem, and this thing has been solved. I mean, we still have this problem with federated, but we no longer have it with gossip. But there is still an issue remaining, serious issue remaining about the learning itself, because you cannot control the learning. It's actually it's random swapping of weights. And this random swapping makes the learning itself go. You don't control how it goes. If you want to customize it, anyone can actually start to inject the environment with some fake weights. And this happens because you actually let go completely of any control of the training, unlike the federated, right? So so we turned our head to a different solution. So we thought, okay, there is some vulnerability in the distributed learning paradigms we discussed. The important one in case of federated learning, you have a single point of failure, because you have someone that decides the aggregation for you. And for the gossip learning, you have more chances of malicious attacks, because there is no control at all of how the learning process should unfold in your network. And that make us that made us turn our head to the blockchain. And why that? Because there are certain points. First of all, the blockchain itself is resilient and immutable. What I mean by that is it's a decentralized way, after all, right? So once a nodes calm down, you don't have to worry about it. You still have the rest of the network. But also, once the transactions or updates are of the model are confirmed, they can be actually stored on blockchain. They cannot be changed. They cannot be deleted. And that solved the problem of something like federated learning, because if the single point of control goes down, you lose the training process, right? But here, no, everything is we keep track of, and that help us with more of a transparency and accountability. So now, because we keep track of everything, we can see who did what. So every action, every update produced by users is actually available to everyone to see and to check. And also, we can actually see what the members are doing. They can be held accountable for their actions. And what I mean by that, you can see if someone share fake data, if they are acting dishonestly or something. And this was a kind of an issue for gossip learning, because we had no control over that, right? And then third, motivation for us why we would consider blockchain is a decentralized controlled learning. What I mean by that, before we had no control at all with gossip, and we had central control with federated. But here we have a control, okay? But this control is in a sense is decentralized. You don't have to worry about the single point of failure, and still there is some control. So you won't have to go randomly. You won't have to have a random learning process, right? And this is, we imagine that this would be handled blockchain through a smart contract that have that kind of model the logic, the business logic we have. In our scenario, it will be the learning logic. So you can do stuff. One of them, it will be verifying which updates should be considered, the vicinity of the updates itself. If it's fake, if it's not, if it should be considered or it's not. We're going to talk about all of that in detail in the next slide anyway. And another fourth motivation for us was the trustless. So we assume that the members that are included in the committee, you don't trust them. So you don't just swap, like in case of gossip learning, you don't just swap your weights with someone else. Now you assume you cannot trust them, and there's a mechanism to consider other weights, and we're going to see that later on. So with this motivation in mind, we got to the point that, okay, now we would like to use blockchain to kind of solve some of the issues of the decentralized learning that we saw in the previous slides. And this blockchain decentralized learning. And this is a problem we considered for our secondment. So we started by two research questions actually to formulate what we have. And the first one, I want to say how to maintain user data privacy, how I make the learning happen without breaking the privacy, which is actually the motivation behind the whole RISE project, right? And another question is, I want to give fair chances to everyone to have a well-trained models. I mean, I give you training. I mean by that, I give you training capacity. I don't have to be worried if I am a newcomer or like I don't have a fair chances compared to big companies. We want to give everyone traceability. You can see which updates are produced by which one, and it's resilient. So you won't have to worry about losing an important point that controls the training in case of federated, I mean. So this is the question we get in mind that led us to this thing you see, this figure you see right here. I will discuss that in the next slide in detail, but you can see that you can take from this picture that we have some kind of environment which is hosted on blockchain, and there is stakeholders. Stakeholders are the model publisher, could be a company or could be an individual. In our scenario now, everyone can provide a model. And we have a data providers, people who have the data, and these people will actually do the training. And we have a third one, which is a committee. The committee are elected from within the community, and this committee are trusted committee. So they are responsible actually for managing and coordinating the dynamics of the environment. I will talk about each one in detail in the next slides. Another part of this architecture is the learning paradigm. How the training itself will happen inside the blockchain. So we kind of have two different schemas. We have one inspired by federated learning and one inspired by gossip learning. So up from the next slide till the end, I will cover these two parts. Who are the stakeholders, what they do exactly in the environment, and how the learning will happen, which is like the core of the environment in a way. So guys, if you have any questions, you can feel free to interrupt me, okay? So stakeholders. The first one we're going to talk about is a model publisher. As we said, it can be a company or an individual. This guy, yeah, let's see what they do. First, it's the training cycle is start by this guy, from this guy. This guy shared the model they created, the architecture to the community, okay? They have to provide some information to with the model. First, they have to provide an initial weight for the model. These weights could be random, or maybe they have trained it locally on some of their data, and they shared it with their model, right? So you have an initial weight and you have the model itself. which you can see in the architecture now on the right, the model and the weights. The point of having the weights because we want to have a common initial state that everyone will consider it, that everyone will start from this state and train further over time, and then there's like there is also another piece of information, which is a performance metric. The model publisher also need to provide that, and this performance metric can be a code file, let's say a performance like a metric file, or can be actually I can code that as a smart contract thing. So everyone who are gonna use this model later and have to access this initial weights, and they have to whatever updates you're gonna produce, they have to check the performance using the same metric. Everyone has the same metric for this model, okay, and that can be triggered by the smart contract. Also, I forgot to mention that the weight itself, the initial weights of the model provided by this guy, by the model publisher, will not be actually hosted on the blockchain, because you can tell that there can be two. You're gonna have a kind of a blow up in the amount of weights if we keep that in the environment. So what happens is that the guy will actually share an address to the weight, not the weight itself. And weight itself will be hosted in an external file system in IPFS. Okay. And then a last more piece of information that the model publisher need to provide to is a validation data set, right? So we need to, this is the one to verify which updates are actually going well, which one are not going well. And these validation data set are, again, not hosted in the blockchain itself. It will be hosted in external file system. And here it will be fragmented. So in a committee, you have the member of the committee, each one of them can access one of these fragments. It will be hashed by the public key of this committee. So the validation data set somehow need a cooperation between all the members of the committee to have an access to the entire validation data set, and no one else can see the validation data set but them, and of course the model publisher himself. Now we go to the next stakeholder, which is the data provider. Once the model is up now to the environment and with all the information we mentioned in the last slide, now the data providers, what they do, first, who are interested, who want to participate in the training of this model, they get to download the model, okay? Then there will be weights produced in the environment. It could be initial weights produced by the model publisher, or like weights produced by other data providers, right? They get to choose which weight to consider and aggregate them. But you should know that these weights, the weights that they should consider only the verified weights. And I will discuss what I mean by verified next slide. The aggregation itself, we will have it done through a smart contract. So I want everyone to do the same aggregation. So before you start training the model, you download the model, you download the let's say the other updates produced in the environment, and then you rely on the smart contract to aggregate them. And you have like one model update that you're gonna use, and then you train this model locally on your data that you have. Be noted that you don't have actually to train. I'm assuming that in this scenario, the data provider is participating in the training, but you felt you can actually just download the model and use it. If you decide to train, you share back the local weights that you produce. Actually, you share back to the environment too. And as before, you don't share them actually, but you share the address to the weight file that is hosted on IPFS, okay? And now once you produce the weights, it will be, that doesn't mean everyone can use it. It needs to be verified, labeled as a verified by the committee later on. Once it's verified, anyone can use them later on, like any data providers who come next can actually download them, aggregate them, as we saw in the first, second steps, and then do what you did by training locally on their own data, right? And after that, sometimes after you share the weights, you might be also required to report which weight files, previous weight files you considered for aggregation, you aggregated before you actually do your training. Sometimes that will be important to share, but that's a matter of detail about the learning paradigm, and I will discuss that in the next slides. So that's what the data providers actually expected to do. And then come the committee, and this committee have a very important, of course, role, because first of all, once the model publisher decide to publish a model, the committee are there. So smart contract, they will be notified of a new model, right, in the environment. What they do, they first check the sanity of the model. I I haven't actually formulated what the sanity so far of the model, what I mean by that, but it can be something, what I have in mind, it can be something ethical. So your model should not break, some ethical requirements or so. Also, there might be a limit on the size of training, right? So if your model is heavily, we can provide in the environment a certain conditions. So if I'm a data provider, and I'm willing to participate in training your model, you shouldn't you shouldn't be demanding on my computer or my machine, right? So this is the sanity of the model. I mean, it's ethical, the size of the training. Sorry, I meant here the time of the training, what kind of data you are asking for, the amount of data you're asking for. So this is I mean by sanity, but I don't have a certain formulation for that yet. Then after that, each member, after the member decide, okay, the model seems to be okay, each one of them needs to have the access to validation data set. And we said it's fragmented validation data set, and it's hashed by the public key of each one of them. That means there will be no single member who has access to the entire validation data set. You have access to your portion of the validation data sets. Okay, that means all the members of the committee will have to cross verify. They will have to work together to verify any future updates submitted by the data providers. And verify in that case, verify the updates in that case will mean for the committee that they check the sanity of the updates. Amount of data that was used given the computational time that it took you to produce these updates is kind of like making sure you're not just, sorry, bullshitting the environment or something. Also, because they have access to validation data set, they get to see the performances of any updates produced by data providers. And finally, they will need to report after they see the updates, they will need to report the validation performance of these updates, right? So it's not like happening. This it's like this job happening over time. So the first 2 or 3 points, it just in the when the model is shared. But after that, the training, all the time of training, when the model is being trained in the environment, you will have to all the time to verify the updates are sensible, and you report the performance, the validation performance, and that will keep going on during the lifetime of the training for the model we're talking about. Okay, and these are the stakeholders we have. This is the now you can see now you can see the architecture, and you can see what everyone actually does. What happened next, we'll see how the learning itself will go inside the environment, right? But here we decide to work with permission blockchain, and we chose a Hyperledger Fabric for that. Verification is done through smart contract, and by verification I mean the checking the performance against the validation data set. If the time of computational time is sensible or not. This is the kind of verification I mean. Yeah, we mentioned that the fragmented validation data set only accessed by the committee, and all the weights and the model itself will not be actually hosted on blockchain. Rather, we have addresses to these kind of data. So now the next we'll talk about the learning paradigm. So we have two different learning framework. We have a federation-inspired learning approach, and we have a gossip based one. So for federation, it will happen in our environment, the aggregation, it's the difference between both of them is about the aggregation. The aggregation in case of federation will be done locally, yes, but there will always be one global aggregation that you start from. So you have to, everyone will have the same state of aggregation. Everyone will, at each at certain time stamp, everyone will have exactly the same weights after aggregation. So that's what I mean by global in that sense. But everyone will do the aggregation locally. Okay, I will discuss that more later. And the gossip learning is different because anyone can have a different version of aggregation. Anyone can do the aggregation they want. So at certain timestamp, you can the data providers or like people who train the model and the environment, each one of them can have his own version of aggregation. So let's start with the federation learning, how it actually goes. So the training starts by the initial weights shared by the model publisher. What happens next is that people like who data providers who want to participate in the training, they come and download the model, download the initial weights. Okay, in that case, now we have let's say we have three data providers. They want to participate in the process. So they download the model, they get the initial weights from you. Okay, that's like level 0, timestamp 0. Each one of them trained locally, as we saw before, on their data, and then they share back the weights. Once they share back the weights, they share actually address to the weights, right? Here comes the committee. The committee will decided that it will consider these three updates from these three data providers, and the committee will verify that. So we have a verification label over these transactions, and we have a validation score, overall validation score reported by the committee over the updates of these three transactions. Okay. Then what happens next? Next time, the next timestamp. Let's say other four transactions other four people decided to come in. They can be the same people, it can be different people, but let's say other four updates are about to happen. What they do, they go back to the last block that was produced, and they will see that there is these last updates, the most recent updates that we have in the system, and these are verified. Okay, so each one of these transactions, each one of these four will get access to, will download these three transactions. Okay, 3 weeks. Previous weights and aggregate them through the smart contract. So at this time, everyone does aggregation locally, but they are using the same aggregation mechanism, and they are aggregating the same transactions because these are the last transaction produced. This is the last update that was produced. So at this time, every one of them will have the same aggregation locally, right? That's what I meant before by a global aggregation in the community. So when they have that, they train it locally, and then they share their like before, they share the weights back to the community. The committee of the community will verify that and report the validation over validation for these four, and then it will continue. Like we have different more and more timestamps and more training. So what we have here is, I call it federated inspired learning. It's not like strictly federated learning as before, but it's more like a federation style, because I mean, in a sense that at each point there is always the aggregation is done locally, yes, but it's like a global view of it. So at each point, we all do the aggregation for the last one. So it's like at each certain point there is one model and one global updates to be considered. That's what I meant by federated. Everyone will take from this. And I mean, everyone the next time step must take from this. And now the local updates are verified according to the smart contract, as we discussed before, as we said before, by the committee. And what we get now is a history, an entire history of imagine that that goes like that much longer and much more transactions. So that would be more of a kind of forward training, like it's like going over time. This is a cyclic directed graph, and the entire history of training will be encoded in your blockchain. Okay, till hopefully we reach convergence. So this is like a federation inspired learning, and you can see it's mostly like it's look like a bit of a federation, right? But it's of course because now we have a blockchain, we do that in a decentralized way actually. Next, we have the gossip inspired learning. So it starts like before with initial weights, right? But here's the difference. First, in the first timestamp, each one come and they download the initial weights, they train it, and they share back the updates, okay? And they to be verified. The first key difference here is the committee will not report an overall validation. Rather, it will be more of a transaction level. So they will report the validation score for each transaction, verified transaction that's considered in this block, okay? And this is the first timestamp. This timestamp 0, this is timestamp 1. And then what happens next, we can have something like this. So in the block, we see that there are transaction or updates verified. But what happened is in this transaction, in this update, the user or like the data provider, before they actually train, how they did the aggregation. They decided to take the three previous verified updates, aggregate them, and use them to train further and have their new weights, right? And this transaction 4. But the story is different for transaction 5, because transaction 5 decided, okay, although I see these people, but actually I'm not going to aggregate from these people. I'm going to go directly to the initial weights and use it right away and train it on my data and produce a new weights, right? So you can see it's different from the gossip paradigm before, because now everyone can have his own aggregation. And if that continue, you can have a plot like this and another plot like this. And you can see in transaction 6, he decided to take T5 and decided to consider T2, these updates, these certain 2 updates only. For the T7, he made a different choice. Okay, so you can see everyone actually it choose which local weights to update from the past, and you can get any previous local updates. It doesn't have to be the most recent block, right? So and I imagine the way that will happen, the way it will happen, or for me, if I decide like I'm transaction 6, I'm decide to consider, I will probably I would consider the validation score that's reported for every transaction to decide which one to take. Okay, I might consider, I might incorporate later some meta information or something about the data provider himself to help you decide which transaction to consider. Yeah, I mean, not also, you don't have also to rely on the validation score. And what we have here also T8 and T9, these people decided to consider these updates, but they are not verified yet. So that's why they are not actually considered in any block. And this is a gossip inspired learning inspired way. And you can see anyone can talk to anyone now. It's not like a pyramid, a strict pyramid like before, like gossip. So it's more like like federated. So what we have here, I mean, the gossip style of which anyone can take width from any block or any step in the past, but also it's not strictly gossip learning, because it's a directed graph after all. So you cannot take, for example, width from the future. You have to take it from the past, right? And what will happen here, the style of training here is a bit different than the federated inspired paradigm, because we do not have one single forward or progressive training. We can have actually multiple convergence happening inside the environment. So for example, people may build feature transaction, feature updates, may decide to build on this T7 because he seemed to be very promising. But others, there was a different thread, different line of training happened happen in the environment with people that decided to actually base their updates on T6. So you can have like 2 fork of training happening, or even more, happening in the environment, and you can end up having two different, like more than convergence, one convergence for the same model. Okay, and I imagine, I think, um, what models will live longer, and what models will live longer, what updates will die, it depends upon natural selection. So the update that's considered and led to a better performance over time, I believe people will consider that more. So you will have more of a natural selection principle in your environment. Okay, so this is the gossip style. It's much more flexible because I do not force people to consider a certain weight from a last update. Anyone is completely free to go back in time and consider whatever they think the best to aggregate before they do the local training by themselves. Okay. So this is a gossip inspired learning. And now there are some insights. I hope at this point you guys are still following, and I hope it's intuitive enough for everyone to follow. So some insights I've been thinking about. First, about the learning paradigm. It's aggregation are done locally, right? But it's one global. But we all have the same aggregation at the time. It seems to be a synchronous approach because all of us have to the next update have to wait for the previous update, right? So it needs to be produced and published first before you take it. So it's mostly similar, I would say, to synchronous approach of learning. It might be slower, but federated is, yeah, it might be slower than the gossip style. Because you have to, I mean, you have one line of convergence that might take time. Okay. I'm not sure about this being slower or not, but I think possibly it might be slower. And it's more type of training because we said it's like there's one thread, one line of training. It's more of a like a centralized approach, but done in a decentralized way. As for the gossip, it's completely decentralized. Aggregation are chosen and even done locally before the aggregation is a kind of chosen according to like a community level thing, right? Everyone have to have the same aggregation at the same timestamp. It's mostly asynchronous because everyone can, in a sense, I mean, that everyone can go back to time and you can start producing your updates now without waiting for like previous one. You can get back to any one time. I mean, synchronous in a way, conceptually asynchronous. That's what I mean by that. And possibly might be faster because you would consider multiple updates from many people, from many updates in the past. So that might be faster training in terms of like there is a wide. I mean by that like a wider field or like capacity for a convergence to happen faster than before. Because in federations based learning, what happens? The one scenario of training that you chose might be might be even faster than gossip, right? But it's only one line. It can be fast or it can be very slow. But in gossip, because multiple convergence happening in the environment, there is a chance that one of them actually can be reached early enough. That's what I mean by faster faster in that scenario. Gossip is more of a highly flexible. I can reflect many different training behaviors in the environment. What I mean by that, many people we decide how the training should work in the environment by ourselves. So everyone will see, okay, I will take that because of some misinformation about the data provider or something about the validation score reported. So that means I'm working more with the one that for example, I would consider a guy who produced multiple updates. I would trust this guy and take from this guy, or I may decide to go with the one that delivers the highest validation score. So the choice you make, your choice about the aggregations you consider is a kind of a training behavior. And it's flexible because anyone can decide to, okay, I want to do the aggregation, I want the training to unfold in the environment in the way I see fit, not in some rigid way like federation. So it's mostly flexible. And if I want to contextualize the learning itself, I want to make the training personalized by each one. Sorry, by each group maybe in the environment. I can see that that can be easily done. That can be easily done on Gossip, but this is more about future work. So from that we get data privacy. Both scenario actually work with data privacy. We didn't want to take data from you, and both of them work with the issues that we said that we mentioned before in the beginning of the presentation. There's possible gaps still in what we're doing because yeah, there is both paradigm, especially the Gossip one. These are like still resilient to malicious behaviors. So I decide to share a false weights, for example, right? And this was the issue of the vanilla Gossip learning from before. But although it is handled in our environment because there is a committee and there is a validation data set, and the committee can see if your updates actually producing something in normal performance or just random performance. So in a sense, we kind of handle the malicious behavior in the system, but still there's a room for false or bad weight injection could happen. And this is not, I would consider this for a future work. It seems as a gap. And also I assumed all the time that the data, all the local data, like everyone have, like all the data providers, each one has his own data, and there is a validation data provided by the model provider, right? At this point, I made assumption. I make assumption that all the data are identically distributed, okay? So that all the training, all the validation have the same distribution, but a possible gap to what if the data are not distributed? Sorry, are not identically distributed. So, I mean, that would be another issue to consider. As for the evaluation, I haven't started. This secondment is just started with Ansopria, so we haven't started experiments yet. And about the evaluation, what I have in mind is that I will compare myself to centralized training tasks. Okay, and I believe that we will take longer time than decentralized. So this is not the strength point we're counting on, right? But what I want to achieve is a comparable performance. So at the end, if you are centralized or I'm doing a decentralized way in blockchain, I still achieve a comparable performance. It would be very, very optimistic to expect a better performance than centralized approach. Also, I'm doing that. The main motivation is the data privacy, but also in this environment, because I now give anyone who has a model, I want to share it. Sorry, I want to train it. He can put it on the environment, and if it got verified and adopted widely by the environment, it's a choice by the people, the data providers. If they decided the model is interesting and they decide to actually train it, then you can scale your training up to community level of training. You have a capacity of all the people in the environment, right? And now it doesn't matter if you are a new starter, or if you're a company that doesn't have enough data, or doesn't have enough, or it doesn't have, sorry, if you don't have enough customers, let's say. So this is the analysis I'm expecting to do. I will be comparing myself to. I would like to see how I can achieve a comparable performance to centralized solution without actually sharing the data, and yeah, and have this hopefully have in big training capacity for everyone, because I would like to assume that we have a decent amount of training data at that time. So conclusion, I'm relied on permissioned blockchain in our work, which is peer-to-peer, to kind of model the decentralized learning like Gossip or Federated. I mean, the vanilla version of them. We kind of try to model that on blockchain. So we call blockchain. That's why we call it blockchain decentralized learning. And my goal was to protect your private data, but also to provide a well-trained a fair chance of having a well-trained AI services to anyone, and the capacity of training can scale up to community level. But there is future work, of course, for what we are doing now. And actually, I would say there are multiple future work. First, there's how to handle the free riders. By free riders, I mean the people. If you have a large number of data providers, they decided to actually download the model and use it, but they did not actually participate in the training. This is a problem of free riders. It's not accounted for in the current work, but it's a future work. So to handle this, there is a rewarding mechanism. This rewarding mechanism is mostly give a reward for data providers because according to how many updates they produced or how many models they participated in their training. And I think this rewarding mechanism, I'm gonna implement it actually in the current work. There is also a reward or more of a rate for the model publisher too. Not only for the data provider, but for the model publisher. Because you might produce you might publish a model, but no one actually adopted, right? For some reason, you just published, and it might actually have some training, but then people decided to let go of this training because there seems this model, because there is another model who might be doing the same job but seems more promising, right? And still, even if you didn't get your model done, you should have a reward, and your reward. I haven't formulated that, but it probably will be about the model and how many people participated, or the performance. I haven't actually decided about this reward. The word mechanism, how it be implemented, but I believe it will be a smart contract thing, so it will be decided by your it's more of a reputation that you get from participating in this environment, either by sharing a model or either by actually training a published model. And an example of what we're doing is it's mostly like a rate on GitHub, or when you participate, if this idea is like implemented in a big scale enough, so everyone knows about this. Like for example, GitHub, then you will have a rate that says this is I participated in this environment, this open source environment, and I did training, or I produced actually models. Yeah, I kind of drifted away from the free rider. Sorry. I'm considering this rewarding actually in my current work, but there is a future work which is to rely on the game theory to kind of make people more engaged in training, rather than actually downloading and using the model without training it, without actually participating in training. Others train for us and we just use it, right? That's a future work. And there is a personalized training. I kind of covered that in the last slide. So how, I mean, my ultimate goal is to actually contextualize the gossip itself, because gossip itself is random, but in what we have now, it's not so random, because you rely on the validation score. So it's more of an informant gossip in our approach now. And I believe that kind of address an issue of the vanilla gossip learning, right? But still, I want to take this to a further step. So what if I can like contextualize the training itself? That means if I'm thinking, if I can have like two different groups in the environment, for example, if we in our domain, like Internet of Sport, right? So if we have two different groups, and we have people who are really professional in training, and others who like amateur, or like we have people who more of an old people and they do that very casual. I cannot give them all the same model, and I want to contextualize that. So every group, I mean, has the scenario of training or a different version of the same model, because somehow they are in the same community. They share something. They share the same context, and that's what I mean by contextualizing the training. And I think that can be easily done on gossip, not easily, but easier to be done on gossip paradigm in our approaches in the federated. I have no idea how I will do that. It's just a future work, okay? And another future work is the malicious behavior. I mentioned that I mentioned that there is a valid verification by the committee and so on, but still you can manage to leak wrong updates or false updates to the environment, right? And here I think we'll rely on some sort of a Byzantine learning to account for this kind of a behavior, but it's a future work, and actually I find it interesting, so I might as well consider it in the future. And there is, they can't work to rely on a permission committee, and this committee, we assume for now it's fixed. So once it's elected, it's always elected, right? It's always there. And these people are trusted. So that's why these people only these people have access to the validation data set. But a future work, what if you want to change this permission committee? There are a lot of issues that will come up from that. How you will do the election, when to do the election, and do you have to change stuff like validation dataset, because all the committee had access to the validation dataset, and that should be confidential. So there are a lot of issues that you would have to put in mind if you want to make the committee dynamic, or actually if you decide to go to a permissionless blockchain. On a security aspect, I believe the weights are shared on the environment still can be, you can reverse that to know some insight about the data. You didn't share the data, but you can know enough about the data, right? And that wasn't considered in the work too. It's a future work for our extension to our secondment. Last one, I didn't account of how you tune your hyperparameters, because we're talking about a model, an AI model after all, right? And there is a training, and there is a tuning for the hyperparameters. I didn't talk about that in this work. I'm not covering in this work. And I assume also the data, as we said before, it's identically distributed. So if they are not, that's also not covered in the work. All of these are part of our future work. Okay. I think I am done, and I hope that was like, I hope you have fun with my presentation, guys. Thank you.
Thank you, Ahmed, for your presentation about decentralized learning. Do we have any questions from the participants?
Okay, no question.
Okay.
That should be a very good sign or a very bad sign. I don't know.
Okay.
Actually, I have a question. If you can go back to the slides about the challenges, where you presented the problem of the free riders.
The free riders?
Yeah.
Okay, I think I presented this here in the future work.
Yeah, exactly. So basically, you're basically saying that you plan to insert some rewarding schemes, and also like to enhance them with some like game theoretical based techniques. But the point is that this doesn't really prevent free riders, right? Like, because you're just rewarding, but you're not using like a sort of stick and carrot strategy where you punish the free riders.
It's true. Yeah, that's true. I just because if you're a free rider, you may have models for free, and hopefully, if it's well-trained models, then yeah, you get an advantage, right? You get benefits, but you will never have a reward. That means it's most of like it will make much more sense if let's say we have this environment, it's now become a thing like a GitHub or something, and then it's a win for you. The guy who participates in training, it's another win for you to say I have this rate on in this environment, right? So I'm actually, you can share the link for your profile or something later on. And I'm not actually preventing, as you said, and I'm not preventing the free riders, but more like I'm giving a motivation for you to not be a free rider. And also make you, if you participate in training, you will get a well-trained model, right? But also I want to give you another motivation, you will be rewarded. But actually this, the game theory thing might directly attack the free riders issue more, because we want to model how we want to maximize how the people can be more engaged. So,
Yeah, sorry. Like usually when you use game theory is basically you need to have in advance some kind of tactics that you can use. So for example, you have two possible actions. Like one action is reward and the other is punishment. For example, that's what how most repeated games work. But yeah, like my only concern is that it's true that. Of course, you're saying that a user may say, okay, I'm getting the model and also the reward, so it's good. But you may have like some users that don't care about the reward and just like get the model for free without giving any contribution.
Yeah, it still there will be a possibility for this. I agree, but you can only try to minimize this.
Ah, sure, thank you.
Thank you. I believe that with the open, it's still after all an open source environment, right? Or open environment. So you will always have this kind of, you cannot. I don't think it's realistic to assume that you will have a free an environment that's free of the free riders. You will always be there as long as you decide to go to an open environment. You will always have these people. This is like a permanent kind of like a permanent issue, but you can only try to minimize it, not to eliminate it.
Right. Do you have any more questions?
Yeah, I have a question. Yeah, I
Who is
have
it?
a question. Ahmed,
yes.
thank you very much for your presentation. It was very interesting. My question is related about the committee that you described earlier. So the way that I'm understanding it is that there will I can see a lot of problems with the trust to the committee and also to the privacy of the users, because also with the cross validation that you described, it seems that they have access to all the data. So basically, both the model providers and the data providers will need to trust um, the committee, right?
Yes. Yeah,
So
we're kind of we're kind of relying on a kind of a proof of trust to for that.
do you have any like idea on how you can prevent this trust, or how you can somehow prevent the committee from having all this free access? Maybe you can, like, I don't know, maybe you can randomize the committee so to change or to be based um, on a rating system or something like that. But this is like, you will not encrypt the data this way. More, um, you will kind of distribute the responsibility among different users to be in the committee. I don't know, like some ideas that I had.
Yeah, I think when we decide to do cross verify, so one way to, I mean, it's a trust committee, but actually I didn't want to put like ultimate trust on the committee, right? So when I divided the data and hashed them by the public key, so you as a member, let's say you are a member in this committee, right? So you will only see a portion of the data, your fragment of the data. You will not see the rest of the validation data. So you will never be able to, unless we decided also, like all the members of the committee decided to, we're gonna work together to hijack the environment, okay? But otherwise, like no one, each one of them, we say that this updates. I report the validation on my portion of the validation data set. Everyone has to do that, right? So everyone produce the validation, his own validation score, and also verify, also check, see the other performances, right? And I haven't actually clearly modeled that still, but I believe you won't have, there will no people, there will be, sorry, there will be no single member that have access to the entire validation data set for a model at a time. That will not be the case. As for choosing the committee, right now I'm going to keep it fixed. But if you choose a committee, it's a permissioned blockchain, right? So we rely on kind of a collaboration work. There is a paper produced by our group too, and I think you might know it. It's called Proof of Trust, and there is, to choose a committee, there need some kind of collaboration between the environment, and there is like a trust score for this committee. So this committee should be more of a someone you can put trust on, and this is a basic assumption we have to make. That's why we went for a permission blockchain from the beginning.
Okay, thanks.
Thank you.
So anyone else?
I wanted to ask a question, very quick one.
Yeah, sure.
So, like for me, that I don't understand the differences between federated or gossip learning. What are the statistical assumptions that you have to make about the data in these three different cases that you are touching? Because you're mostly into like the technology, like data transferring and all of this, like transferring of your weights. But what about do you have to make the same assumption for all these three different techniques about the data?
In our work, yes. In our work, what I believe a strong assumption that the data are again IID, right? And this assumption is assumed for both scenarios. But if you're asking about the vanilla, the original gossip federated learning, I think this IID problem might not be a problem might be less of a problem for the federated learning. But otherwise, you don't have statistical assumptions, no more statistical assumption about the data.
So you don't do anything when you get the data, you just feed them as you do in a normal.
Yes, yeah, I don't get the data. I do not collect the data to do something with the data. It's mostly right now I assume they are like on a similar distribution. That's the only assumption I can make right now about the data. But after all, it's private data, right?
Sorry, Hamid, can I ask you one more thing?
Sure.
Why do you need to make the assumption that the data are independent and identically distributed?
Because if they are not, then the training I don't believe the training will be okay. I mean, if I take the model, the weights are produced from training on a data with certain distribution, and I apply it on my data, and my data has different distribution, and then I report some kind of a score, and then the committee has a validation data with a different distribution, and they report a different validation score that doesn't actually match the one you produced on your own data, on your own local data. So physically, the training will be inconsistent.
Yeah, but I mean, now you're talking about like the difference between training and validation data, but like, do you also need to assume that each user has like data that come from the same distribution, like that basically you have 3 users participating in the training and each of them needs to have the same distribution of the data?
Yeah. This is the assumption we're making right now, but yeah, but I mean, there is a need to make this assumption, right? You need to make sure that the training is not going to be hindered because of a different distributions, and you can only assume that, or you can actually work on that. And right now, I mean, I didn't consider how to handle this issue.
But if I can step in on that, is that
Sure.
you have like 2 different scenarios where IID is violated. It's like when you don't have independent data, and in that case, you cannot feed the data one by one in the training process because the gradients are not independent anymore, but they are dependent. And the other case is when you have a shift of distribution. So you have like, they are independent, but they are not identically distributed. And in that case, if you are feeding a data that belong to a particular distribution, it has high likelihood on that distribution, but you are treating it as it comes from another distribution where the likelihood is low. And the gradient should be weighted according to the probability mass that that particular data is coming from. So if you don't correct for that, then the gradients being produced are inconsistent.
Yeah, sure, exactly.
I don't know if that makes sense, Thomas.
Yeah, sorry. I mean, it's a little bit to follow, like, so you know, very, very detailed examples, like via you know, without seeing them. But yeah, I mean, I sort of see your point, but like, for example, like I think that the point of using things like generated learning, sorry, federated learning or gossip learning is actually to use data that are coming from different data sources and that actually follow different distributions. That basically they add new information to the models. Like that's, I think that's the point. But yeah, I'm not an expert, so maybe I'm wrong.
Sorry, Ivan, sure. Please go ahead.
I'm not familiar with federated learning. That's why I was aiming to ask you. But in theory, like what I usually like when I'm dealing with such or when I'm reading such paper, what they do is that, of course, like you have a distribution for one particular source. What I'm imagining now is that you have a distribution for one particular source and another distribution from the other source, but you treat them as having a same distribution, which in itself is multimodal. That's the only thing I can think of in this case. Like if you have like two different sources, but they have like a normal distribution, but different means, but you treat it as a single distribution, which is a multinomial Gaussian. And then you have to take that into account, how to correct the gradients in that case. Because if you are not identically, if they are not identically distributed, then you cannot, the likelihood that you are maximizing is not going to make much sense, because you are either maximizing the likelihood of one of the sources and then disregarding the other, or the other way around. But if you take them all two together, then the likelihood that you are estimating at the end should make sense.
Yeah, but
I mean, what you're trying to optimize in the end is like a sort of overall underlying distribution that you're assuming that exists. Like that's the point. But that's always in machine learning.
Yes, because you're trying to get a good distribution of your labels, right? If you're doing prediction, and then if the labels it's a conditional distribution given the data, and if you have a bad conditioning there, then the distribution of your labels, yeah, I mean, there are so many ways it could go wrong, but once again, I'm not too much familiar with federated learning, so I'm not gonna add too much noise on that.
Yeah, for me, I'm kind of new to this decentralized learning, so I cannot really tell much about if it's a basic assumption or not. I don't know if everyone who does gossip or federated they work with the non-ID data, but I think I cannot check that right now. I really do not consider it in my scope, in the current scope of work. So it's interesting actually to. I would like to do some literature about this.
But if you have a data dependent, you can like pre-process, kind of like you can rotate them to make a bit of independence, but you lose some information as well. So there is a price for that.
You mean by rotating them? Like I control which one has which distribution from the beginning, or you mean rotating it for the same data provider?
I mean, if you imagine that you have a 2D Gaussian distribution, right? but they are X and Y, but X is dependent on Y, then it's going to be some kind of a cylinder, right? I'm sorry, elliptical shape on 2D space. But if you rotate this elliptical shape, okay, that you get the perpendicular axis along the axis of the cylinder, then you get a 2D Gaussian distribution, which X and Y are independent in this case, because you can write this a product of one another.
Okay.
And the covariance matrix now it's a diagonal. It's not it doesn't have any non-zero element outside the diagonal. And you could do something the same with the data, but of course you have to do some information there.
Also, one problem with this kind of statistical approach is that you need to know the data, and that kind of goes counter to the fact that the data of the providers is private. So you have 1,000 providers, but you don't know which ones have what kind of data, because that's the entire point, that you don't know that. So you have your model kind of having to learn from that, but without being able to know specifically what distribution is at each guy. So it's hard to use these techniques to kind of counteract the non-identical distribution. However, I can tell you that for gossip learning, there is very little research that cares about it, but I'm sure there is at least one paper when they show, not theoretical, but experimentally, that it still converges. It might take longer, but it still converges correctly, even when the data is not identically distributed. And for federated learning is basically a parameter server architecture, just on larger scale. And in a parameter server architecture, there is plenty of literature on that and on how it works with non-identical distributed data. I'm not an expert on that, but I think most of the results that have been done for parameter server architecture can apply to federated learning. Problem is, typically in parameter server architecture, you can shuffle the data. In federated learning, you can't. So you have this limitation, but otherwise, I think most results can be taken the same. So I don't think, honestly, it's a big problem, the fact that data is not identically distributed. But yeah, it might also depend on what kind of model you are training on it, if it's very sensitive to this. Because in gossip learning, for example, you will have like different batches with completely different gradients. Over time, it still converges, typically, according to experimental results. But again, maybe with some models, this will cause issues.
It will be actually interesting to try to, to explore this.
I think it will be fine if you're just after the accuracy, but if you are after something else like calibration and stuff, probably, I don't know. Accuracy should be fine even if it is not IID, I think, but I don't know.
I cannot mix. I really cannot. I only can assume it. They are IID. I don't know how they will affect. I cannot tell if they are not, how this gonna affect the training. But I believe it's a matter of it's a matter of how the updates happen in the system and what kind of models you are considering. What's the task load?
Because my only worry here is that if you have one source that produces 95% of your data and you have another source that produces 5% of the data, I think the model is going to be quite good at predicting data that coming from the source where the majority of the training data pool comes. And when it comes to like trying to predict correctly on the other node where you have only 5% of the data, I think the model might not be as good, I think.
Yeah.
That's my only worry I have in these cases.
But perhaps one way, if I want to really address that, I may ask some kind. It might be a bit of leaking for some, but I can have some statistics about, maybe not the data, but some statistics about the data. But still that would be risky. Security-wise, that would be huge leaking.
yeah, what as Ludovico was saying, it's a bit hard here because, I mean, in federated learning, that's the whole purpose, right? Not to gather the data at the same place, right?
Yeah.
Yeah.
But I'm now assuming it won't be a problem, even if they are, even if they are not. I need to see what, because if you have an environment and you open, and you can have any kind of models there, and it would be hard at least for me to predict what kind of performance you might get, and right now I only can assume they are identically distributed. But thank you guys for the comments. Actually, they are very nice.
So do we have any more questions? Okay. Thank you all for participating in this 5th race online seminar for 2021. See you in 3 weeks with the next.